right, we are finally ready to actually apply our method of steepest descents to the Hankel function. We've mastered the Laplace method of Laplace, so we've mastered the method of stationary phase, and we're going to put them together and execute the method of steepest descent on the regular Hankel function, which will then tell us through our relationships the method of the asymptotic form of the spherical Hankel function, right? So we've got this thing all set, and in the last lesson we actually came up with a contour representation, or I should say an integral representation of the regular Hankel function, and it is a complex integral. It is a contour integral in the complex plane, and it has a very specific form, namely this form right here, right? This is the form that we need to execute the method of steepest descent. An integral in the complex plane with a complex variable of an analytic function times e to the x times where the argument of the exponential is x times another analytic function of z. And notice that this is some function of x, and in our case it is the Hankel function of the first kind, nu, right? That's the one we're after, of order nu. That's what this is, right? The Hankel function of the first kind of order nu, function of x, equals this. And we've indicated the contour with these weird limits of integration, but let's remember what that contour integral actually is. We have our real axis, and this is the branch cut. It goes from the origin, which is where the dot is, to negative infinity. And we are interested in leaving the origin, going above the branch cut, and to negative infinity, asymptotically approaching the real axis from above. And that will be the contour associated with the Hankel function of the first kind, meaning we integrate this integrand, the integrand that we had found in our last lesson, along the contour I just drew, which is sort of symbolically indicated as the origin plus a little bit to minus infinity plus a little bit of imaginary amount. Actually, we can almost, in principle, I think, get rid of this plus I epsilon down here and just say from the origin. But the point is, you can't articulate the actual contour in this in this notation. You have to draw it. So we have to draw the thing out just like this. But anyway, the point is that now that we have it in that form, we can now execute our method of steepest descents. And we can do it two ways. The first way we can do it is the way we left it off at the end of the last lesson, which was we had produced literally a formula, right? A formula that tells us what the asymptotic form of our function is. It's going to be the function g evaluated at the saddle point times e to the x times f evaluated at a saddle point times e to the pi minus beta, where beta is defined through this function here, and then you have the second derivative of the function, that's the argument of the exponential, evaluated at the saddle point, and then you have the square root, 2 pi over x. You got all this stuff in there, but it's kind of formulaic. The tricky part is to make sure you got this correct, right? You've got beta correct. And this is so formulaic, you've got to try to remember, okay, what are all these things? All right, theta, that's the angle that we go through the saddle point. All right, cool. What was beta? What was beta again? And you kind of got to go back and remember, okay, well, beta was, how did we derive this? Well, we found that the second derivative of our analytic function, the one that's in the exponent, the second derivative of that thing, we're going to call it a magnitude. We're putting it in polar form, and it's this argument of the polar form that defines what beta is. So you have to evaluate this in order to know what beta is. And so our first approach for this is we could just take the formula that we got and struggle through it. Now, it's not much of a struggle, but execute it and see what we get. So let's do that first, okay? All right, so the first thing we're going to do is make sure that our Hankel function, right, which is defined through this contour integral, matches our criteria, and to set up a one-to-one correspondence between the criteria for the method of steepest descents and the form of this Hankel function. And not a problem, not hard at all, because this guy right here, right, that becomes g of x, right? That's an analytic function of a complex variable v. And then we have this 1/2 of z minus 1 over z, and that is analytic function, and that's f of z. And then we have the exponential x. We have that right there. So that's all good. We are executing a complex integration, and we have our contour integral. So we have fit the form, and notice that this is all x is greater than 0, and that's also part of our understanding here. So we have our function g. Let me see. Our function g, check. Our function f, check. Now we will calculate f prime, which is very, very easy. Because f is analytic, we can just go ahead and take its derivative. And where this derivative equals 0, where f prime equals 0, those are the saddle points. We know they won't be maximum points, and they won't be minimum points, because in the last lesson we learned about the method, or about the maximum modulus principle, right? So we know it will be a saddle point. And so the saddle points for this show up at plus or minus I. So we need to know that. And then the second derivative of f is pretty straightforward. It is minus 1 over z cubed. And if we evaluate that at a saddle point, we get, at the saddle point I, for example, we end up with minus I, which is e to the minus I pi over 2. So right away we see that this is the beta. Pi over 2 is the beta, actually minus pi over 2 is the beta, right? So I guess I could write beta equals minus pi over 2, based on the way this is all defined in our formula. But this is what we need to sort of get through the formula. We need to know the saddle points, and we need to know these functions. Now, our contour has to go through the saddle point, right? So if this is our contour right here, we have to make sure that we leave the origin tangent to the line, come up, and then this is the origin. So this point right here, I, has got to be right there. And our question is, what is the angle? What angle do we take through I, right? That's the point I. And that angle will be theta, right? And we don't know what that we don't know immediately what that angle is, but we have our method. We know we've deformed our contour so that it goes through the saddle point. And the reason we've done that is we have we're going to go through the saddle point in such a way that the phase is stationary, which means that the non-stationary parts of the integral will all cancel out. So everything out here is going to sort of cancel in the integral, and everything out here is going to cancel in the integral. And we're basically pushing it so that the entire contribution of the integral is kind of all focused right there, especially for large values of x. I mean, that's the whole point of all this. So, if we had, we'll get the same value if we do an integral that looks like this, but now the value of the integral is kind of distributed all over at different places. And it's probably still pretty chunky, right? There's still places where the phase will change a lot, and those sections will cancel out and not contribute much. But there's probably going to be phases where the phase changes much slower, and they do make contributions. The point is in this circumstance, we're going to go through the phase is absolutely stationary right there. And because the integral also has a real value that's peaking, the entire value of the integral gets concentrated right there. And ultimately, our integration goes right along this line to infinity. So with that in mind, let's just go ahead and do our plugging in. Okay, so here I've set up our formula, right? This is the formula that we've developed for this very complicated process. It's really kind of remarkable that it comes down to a formula like this. But once we've decided, the formula only applies if we've decided to drive the contour through one of the saddle points. So the fact of being driven through one of the saddle points is already sort of embodied in just the fact that we're using the formula. The formula is only derived for that case. And it's right in here, right, where, this is the complex function evaluated at the saddle point, the exponential evaluated at the saddle point. Beta is this this second derivative evaluated at the saddle point, the phase, the minus pi over 2 phase. So the fact that it's at the saddle point is already captured just through the derivation. Here's the second derivative at the saddle point. So one thing I noticed before I was going to start this derivative or this process is when I went over here and I took our formula and I established each of our correspondences. This GZ corresponded to Z to the minus nu minus 1, for example, and F 1/2 Z minus 1 over Z. I actually left off a prefactor, which is important. Right? If you look, you'll see there's a 1 over I pi. That belongs as part of G, right? So when I write this G down, I really need to include 1 over I pi, right? Which ends up making this what? It makes it a Z to the minus nu minus 2, right? 1 over pi, like that. So that's what G really is. And that's important because we're going to start plugging in those substitutions here. So for example, we will immediately plug in 1 over pi I to the minus nu minus 2 for G. That is G evaluated at the saddle point, because the saddle point is I. And then we substitute for the exponential, right? X over 2. And again, note that this is evaluated at the saddle point, and the saddle point is I. So it's, instead of Z minus 1 over Z, it's I minus 1 over I. Then we evaluate this exponential, pi minus beta over 2, right? And we've decided that beta is derived from the argument. What is that called? What is the, I think it is called the argument of the complex function, because it's, regardless, it's the phase of the polar form, which is minus pi over 2. So we make that substitution, right? And so we get pi over 2 minus pi over 4, right? This is the pi over 2, right? It goes like, let's see, it goes like this. This pi over 2 is this pi over 2. Beta is minus pi over 2, so that's minus pi over, over 4, right? Okay, so, and then this one's very easy because f double prime evaluated at the saddle point is just minus I, because e to the minus I pi over 2 is simply minus I. It's the polar form of the complex number negative I. And so we have this. Now notice, look at here, we already have our square root of x in the denominator, which really is important because we kind of know what the asymptotic form answer is for the spherical Hankel function. And we know we'll need a square root of x there to make that happen. If you don't remember, we'll be reviewing that. We'll get there, right? We'll get there, so you'll see it. So now it's just a matter, I mean, it's there. This is the answer. This is the asymptotic form of our regular Hankel function is this thing. So now it's just a matter of stretching it out and simplifying it as much as we can. And so we do that, right? This simplification here, let's see. This simplification here, this minus, that's just, that's me taking this and putting it in polar form. So I've taken this and I put it in polar form. So I becomes e to the minus I pi over 2. What happens to this 1 over pi, though? I think this 1 over pi is supposed to come over here, enter in as pi squared, and then a pi should appear in the denominator. but I didn't do it. I kind of made it sort of disappear here. Let's see if I remembered to put it back in. If I didn't, we'll have to go fix it. Then there's this, well, all right, we should definitely fix it right now at least, right? So then what do we do? So then there's this guy, x over 2. Well, I minus 1 over I is just 2I. So you have this 2I here. And here you see this 3/4 pi. So that's this guy. Pi over 2 minus pi over 4 is I to the 3 pi over 4. And then you have the factor there. And what's our next step? Let's see. The next step is this thing. Oh, yeah. So here I put the 1 over pi back in, right? I just dropped it in this one term, and I can't put it back in because I'm undoing other work, so I always end up undoing my 1 over pi. But regardless, there it is. It's back in, and now I'm taking these exponents and adding them all together, and we get the ix is from here. The 2's cancel. The I 3 pi over 4 is from here. The minus I pi, that comes from this term. That comes from this term multiplied by that term, and that becomes that. And then this guy is the I pi over 2 times nu, right? Obviously becomes that guy. And what else is happening? Oh, and then I move the 1 over pi. So this is going to suddenly appear under the radical in a moment, I suspect. All right, so then the next step, is just squeezing these things together a little bit, combining the 3 pi over 4 with the minus I pi. You get minus I pi over 4, you get minus I pi over 2. You put in the pi squared down below, and then you end up with this guy here. And I'm pretty sure, that is it. So this is the answer, right? This is the asymptotic form of the Hankel function of the first kind of order nu as a function of x. Notice it's all a function of x. You know, the z's are long integrated away, so there's no more complex stuff. So this is all a function of x. But it's the asymptotic form. So I guess I should be writing, I don't know, is there a symbol for asymptotic form? Let me check. Hold on one sec. Let me look. Yeah, I remember it. The generally accepted symbol for asymptotically equal to is this. Not 2. It's 1 with a wave on top, right? So a tilde and a straight line. So that's the answer, right? And now, if we take that answer and go back to the beginning, where we understood that our spherical Hankel function of the first kind was literally defined through our solution of all the differential equations as the square root of pi over 2x times the regular Hankel function of the L plus 1/2 order. So we want the Lth order for the spherical. It's defined in terms of the L plus 1/2 order. But now we know, so we're looking for the asymptotic form of this. Well, that's just a thing. It is its own asymptotic form, but we now know the asymptotic form of this. So the asymptotic form of this is going to equal the square root of pi over 2, right, over 2x, that's this term, and it's going to be the asymptotic form of the spherical Hankel function of order L plus 1/2. So what we do is, this was the solution from our previous work. Nu, right here, the order was in terms of nu, but now we substitute for nu L plus 1/2, right? And we just get this guy right here, and then we just crunch the numbers, right? We have, the e to the I, e to the ix comes right down, the minus pi over 2L comes right down, and then the minus pi over 2 times 1/2, which is pi over 4, minus another pi over 4 gives us a minus pi over 2. And with all those in place, we end up with this expression right here, which, by the way, is the expression that we know is the answer from all of our textbooks, right? Where they just compress they factor out a pi over 2 here and get an L plus 1. So we've got our answer for the asymptotic form. We now own the asymptotic form of the spherical Hankel function. And this is great, right? There's another form where if you pull out this minus I, but this is the form you see in most textbooks. But look, it's got this 1 over x dependence, which means this thing is driven towards 0 by this 1 over x dependence in the large x limit. But it also oscillates, right? It's got a real and complex oscillation, right? So it looks exactly like we would expect it to look. That is just like those graphs we showed in the earlier picture, right? The amplitude of these things goes down as 1 over x in the asymptotic limit. Now notice the behavior down here, this behavior where it starts at 0 and starts driving up, and for the larger and larger Bessel functions, this behavior here in the early part, that's not captured in our asymptotic limit. Although I guess we haven't really discussed yet the J and the Bessel, the spherical Bessel function of the J type and the Neumann type. But that's not really a thing, because these two types, the J-type Bessel function and the Neumann-type Bessel function, which actually are the ones that show up in our work, those guys are just defined as a linear sum of the two Hankel functions, right? We're not going to go through the Hankel function the second time, which is just the lower contour, but you end up with this answer, and you combine them together and you get a sine and you get a cosine through the fact that you have these two exponentials. And of course, it's the usual thing where the complex parts cancel or the real parts cancel. But you'll see that for this Bessel function, if you look at this, in the small x limit, it blows up. It makes no sense when x is small. But of course, it's only derived for when x is large. So we can call this done in the sense that we kind of own it, right? And we've done the work to believe that we understand these asymptotic limits, and we now feel like the complexity of the Hankel function is not being swept under the rug by our textbooks, who suddenly replace this very sophisticated power series solution to an exotic differential equation with just some wacky exponential. That replacement, we own it. And God, I spent a couple hours on it, I'm not going to lie, probably more than most of you think it deserves. But for me, these things just really stick in my craw, right? I always feel like, oh, okay, I'll just read on and someday I'll go back and figure that out. Well, you know, I did, and now I forced all of you to do it, for those of you who followed through. But this ownership of these little concepts along the way, that's what makes the difference, because lack of ownership of little concepts adds up. And it starts detaching you from the work. So you really have to get in there and find the time to figure this stuff out. Okay, so let's move on. And by move on, I mean let's just drain this whole story dry for everything we can learn a little bit about complex analysis here. If you're happy with what you know, the rest is just we're going to kind of explore a little bit about this asymptotic process beyond the formula. I want you to see a little how this thing actually worked and demonstrate some of the stuff that we saw when we studied our complex analysis in general in like the last lesson. But this is a plot of the magnitude of the complex function that was in the argument of our exponential. And you'll see that indeed there are two minimums, right? There's a minimum, let's see, what color should I use? I guess black. There's a minimum here and a minimum there. And it's 0. The value of the function is exactly 0 there. And you can see exactly where that would happen, right? When z equals the 1, just the real number 1, you'll get 1 minus 1, which is 0. And same with when z is minus 1. So these are the two minimum of the function. There is, however, no maximum. What would happen is as we go off in these directions, the function is unbounded, right? It will go up forever and ever and ever. And you can also see there's saddle points right here at I and minus I, right? So you can literally see the saddle points at I and minus I. So now our contour actually goes, it leaves 0. It leaves the origin, and it sort of follows this thing. It goes up this saddle point, then down, then behind this thing, and then all the way out like that. So it really does follow this. Well, that's the contour we needed to integrate. So the question is all of our work was really to force the integral to have only a value right around there. And the question is what was the path that we took through that point? What direction did we go? And we called that direction theta. And we decided that theta was going to equal pi minus beta over 2, and we figured out what beta was from our formulas, but it was the phase of the second derivative of the function evaluated at the saddle point, and we ended up with 3 pi over 4. So that tells us that this line here is we're traversing through this saddle point at the angle theta equals 3 pi over 4. Let me see if I can draw that. Let's see. Well, this angle here would be 0. This would be pi over 2. So 3 pi over 4 would actually be an angle going off in a 45-degree angle in this direction. So I've drawn this exactly wrong, right? If this is our saddle point, we have to make sure we go through it like this, right? And then it goes down and out to infinity. So where's our saddle point? Kind of hid it in here, but I think right there. So this is the direction we actually go through. And then, as we've already sort of seen, basically, the point of that is that's where we get stationary phase. And this is the graph of the real and imaginary part. This is the imaginary part of our function f of z, and this is the real part of f of z. And what you'll see is and this is designed so that we're going through the point at an angle of 3 pi over 4, right? So, and you'll see, right? Look at the imaginary part. The imaginary part does exactly what it's supposed to do. It goes up, it levels off, so it's totally stationary right here, and then it starts to change. And the real part does exactly what it's supposed to do. It actually peaks right, it has a local maximum right at I, right? So I has now been shifted to the origin of this system, right? So this is all about the value of the function around I. In other words, we made the substitution z equals I plus r e to the I theta. We've chosen theta, that's our direction, 3 pi over 4, and r is the only thing that's changing here, right? So we changed, so r, so that forces you to go through the point I in a straight line, right? And when r equals 0, z equals I, right? So that's what we're doing here. But the point is that the real part maxes out, and it's a shallow maximum, right? This isn't, this could have been something like, like really pointy or something, but it's not. It's shallow, but that just means that x in the asymptotic form just has to be large enough so that this peaking just really drives this whole thing into being, drives our contour integral into being a Gaussian right there. And the reason that Gaussian has to be right there is the phase is stationary, so it's actually contributing to the integral. And even though the real part gets really big out here, the phase is changing so much that all this contribution just cancels itself out and doesn't really contribute to the integral. Now, the problem, though, is that you can actually satisfy this two ways. Remember, beta was equal to the magnitude of the second derivative at the saddle point times e to the I, that's not what I meant to write. I meant to write that the second derivative evaluated at the saddle point put into a polar form looks like this. And beta is what we get out of that. However, beta has an ambiguity to it, right? If I've calculated that we calculated beta was minus pi over 2, but we could also make it to be 2 pi larger than that or 2 pi smaller than that, right? Because you have that choice, right? You know, beta plus 2 pi is going to give you the same ultimate polar answer. But if you do that substitution, if instead of minus pi over 2, you wrote minus pi over 2 plus 2 pi, right? This would end up being well, actually, it'd be minus pi over 2 minus 2 pi, right? Let me get this right. Right, so now we choose it to be minus pi over 2 minus 2 pi, which ends up meaning that beta is now minus 5 pi over 2. And if you plug it into this formula at minus 5 pi over 2, you end up with pi over 4, right? Yeah, I think so. You have pi, whoops, you have pi, and then this minus pi over 2 is now minus 5 pi over 2, so that's 7 pi over 2. And 7 pi over 2, you just scratch it back to being, it's equivalent to pi over 2, and that's pi over 4, right? So it's all pi over 4. So you end up with pi over 4, and that satisfies this expression. But here's what happens. If you try to go through the saddle point with a direction of pi over 4, which is what this expression is, you still get the stationary phase because this criteria was designed to give you stationary phase. The problem is that the real part actually has a minimum in it. It's a minimum real part. So this part contributes very little in principle to the overall integral. So it's the wrong direction. And what that is tantamount to doing is, if you go back to this picture, that's tantamount to going, instead of over the saddle point, you're actually kind of going like this. You're going, let's see, pi over 4, you're actually going this way, and you're kind of climbing up these hills, right? You're climbing up these hills instead of going down these hills. So, so anyway, that's kind of showing you that there is a bit of caution you have to do in just exercising this formula. If you choose beta wrong, it won't work. So a rote application of the formula is probably not the way to go. You probably want to make sure you sort of decompose things and study things a little more carefully. But these two graphs are really, this is the graph. This is what you're after, right? This is the goal of the stationary phase method. And the stationary phase method has a lot of relevance, right? The path integral formalism of quantum mechanics really has to do with finding out places where phase is stationary. The WKB approximation does that. There's lots of places where this notion of stationary phase is really, really critical. And so this is totally worth doing and understanding in detail. Okay, all right, so that does wrap it up for us. We now take our ownership of the Hankel function, or I should say our ownership of the spherical Hankel function, and now we treat it as though we just bootstrap it right through this. We own the spherical Bessel function and the spherical Neumann function, and now we are going to get onto the subject of plane waves, which are also critical prerequisite stuff. We're going to talk about the decomposition of plane waves into its partial waves, and that's a really, really beautiful subject, and I'm excited to get into it. So with this ownership in mind, this is under our belt. Let's proceed. I'll see you next time.